Hello everyone, I am Saiswam Patnaik, a third year BTech student, and today I will be giving you a seminar on the topic which is widely used nowadays in the field of natural language processing and has grown exponentially in the present era. So imagine a scenario where you are in a place and you are not able to understand even a single word due to language difference. Nor you knew the local language, nor the locals could understand your language. So you took up your phone, opened Google Translator and typed whatever sentence you wanted to translate. The translator took some time and performed the computation and displayed you a result which is well translated. These all comes under the practical implementation, but have you wondered a sentence which could not be processed by the human brain could easily be processed by a smartphone and displayed you a well accurate result. So how does this magic actually happens? There are different sequential models which helps in processing natural language and helps us in getting meaningful results. One such is RNN, which is a popular sequential model which can perform NLP tasks and has shown effective and great performance for sequential input data. Current neural networks are basically derived from feed-forward neural networks where the output of the previous stage is passed on as the input to the next stage for further computation. They are far different from the traditional neural networks where the input passed and the output we get after processing are completely independent to each other. But in RNN we need to predict the next word as output by taking the context of the previous word in a sequential data. RNN gives rise to three different types of architecture like vector to sequence model which can perform tasks like image captioning. Here the given input image is first converted to a vector or matrix and then passed into a convolution to extract the feature, and this output is then passed into the RNN network which finally produces a sequential output for describing the image word by word. Now second architecture, sequence to vector model. Sentiment analysis kind of tasks are performed using this architecture. And sequence to sequence model, this model is used to perform language translation like converting from English to Hindi or Hindi to English, etc. But in some circumstances RNN become a hazard and a complicated network because it's too slow to train. And in various cases where the sequences are too long, then the RNN results in vanishing gradient problem due to which the last neuron don't get trained properly and it forgets all the previous data from input data. So this gave rise to a LSTM network known as long short-term memory. It contains different branches that allows the information to get passed on to the next stage or next cell without much processing in the current cell. So this helps us in reducing the vanishing gradient problem, and also it can store a large amount of data, large sequential data in its memory for a longer period of time. But the architecture of our LSTM network is too complex and is more complicated than RNN, which makes it even more slow to get trained. But that's not the issue. In the present era of parallel computation where everything is getting parallelly trained and computed, LSTM networks use sequential computation where we needed to pass the data sequentially as the current state processing required the output of the previous state. So this flow did not make any use of the today available powerful GPUs, which is well designed to achieve faster speed by going parallel computation. So can you think how can we achieve parallelization in sequential data? If yes, then congratulations, else no need to worry, cause is the title of this video. In 2017, a deep learning AI research team of Google did a brainstorming session and introduced the transformer architecture to the world. The transformer model uses an encoder-decoder architecture very much similar like RNN network, but the fact that differentiates it and makes it outstanding is the attention mechanism, which provides a meaning and context of the word for any position in the input sequence. Unlike RNN, where we pass on the input sentence word by word onto the encoder and the current word's hidden state contains the previous word's dependency, ultimately producing a single word embedding at a time. But transformer don't process the data serially. We pass the complete input sentence and get the word embedding simultaneously, reducing the training time to a great extent. So how is it actually working, or how the mechanism actually works? So let's understand each part or each component of the transformer architecture one by one. Coming to the first part, unlike human brains, computer cannot understand every form of data which is provided to it as input. It can only understand numbers, vectors and matrices. So when an input is provided to it in the form of text, then we map each word in a space where words having similar meaning or similar context are placed closer to each other. So this space is basically called as embedding space, and the result is a vectorical representation of all those words numerically. So there are many pre-trained word embedding space available online, which we can use for training, like the globe or what to whack and etc. But the issue which got popped up during the embedding is that a single word can have multiple meaning when used in different sentences based on its placement. So how to deal with this problem? This led to the insertion of the positional encoders. Positional encoders return a vector which stores the information regarding the word's position and its distance with the other words. So by it mainly uses a sine and cosine function to perform all these kinds of computation. So coming to the second block, the output of the embedding and positional encoding layer is then passed on to the encoder network, whose main role is to map the words into a continuous representation that holds the information learned for the entire sequence. The encoder network mainly contains two submodules, that is the multi-head attention layer and the feed-forward neural network. So before moving further, let me explain the most important mechanism used in a transformer architecture, which I already mentioned above. This mechanism emphasizes on each and every word and gives us the answer of the question which part of the word should be given more importance and how much importance should we give to each word. For example, let's take a sentence, the big red dog. In attention mechanism, we will get the information about how important is the ith word as compared with other words in the provided input sequence, or in this case the big red dog. Moving deep into the mechanism, we pass each word to three fully connected layers to create a key, query and value vector. Just like you search something on Google and by entering a query, and that gets mapped to a set of keys and to provide you the best result or value or best article. The key, query and value vector in attention mechanism also works in the similar way. The query and key vector undergo dot product computation in order to produce a metric, which is basically the attention score of the word as compared to other words present in the sequence in a particular time stamp. Whenever we perform dot product between two vectors, the result can sometimes become too large. In order to normalize the score and bring it in the same range, the square root of the dimension of the key vector is divided to each score. So after applying the softmax function on the processed matrix or processed score, we get a general score between 0 and 1. The highest score gets close to 1 and low score gets to 0, ultimately making the model to analyze the word more confidently and assign its importance correctly. So now this vector is multiplied with the value vector present in order to get the main output vector from the attention mechanism. So more the score is closer to 1 in the final output vector, the more the algorithm will give emphasis and importance to that word, and vice versa. In this case, we only used a single key, query and value vector in order to perform all the computation. But if we split these into multiple vectors before processing, then it becomes multi-head attention, where each head represents each pass of the complete computation. Each head produces a vector which then combined and then passed it into a linear layer for further computation. The multi-head output vector is then added to the output of the positional encoding layer, which is called a skip or residual connection. You must have heard of ResNet 50 layers or ResNet 50 network, ResNet 100, ResNet 150. These all works in this skip connection flow. So basically, skip connection or residual connection basically helps in reducing the vanishing gradient problem while back propagation or weight training. So this output is then normalized using layer normalization and then fed into a feed forward neural network consisting of linear layer and ReLU activation function. Again, the output of feed forward neural network is added to its input and then normalized, which gives it a better and rich representation. So this sums up the transformer encoder whose output is properly processed and give us a continuous representation whose attention score will help the decoder to focus on the most appropriate word, ignoring the unnecessary word by which can affect the accuracy. So we can even stack the encoder multiple times for encoding the data data, which boosts the predictive power of the transformer architecture. Now coming to the second half of the network, let's take a deep dive into the decoder network. Suppose example we want to translate from English language to French language containing the above example input sequence, the big red dog. The French translation of it is les gros chien rouge. So now we need to feed the French sentence into the decoder, but as I earlier said, computer cannot understand textual data or string data. So this sentence is also passed on to a embedding layer and then into a positional encoder to retrieve the positional information of the words present in the French sentence. The vector output is then passed as input to the decoder network. The decoder block contains three sub-modules. First is mask multi-head attention, then multi-head attention layer, and the feed-forward neural network. The first block, that is the mask multi-head attention, is very similar to the multi-head attention layer, but works little different. Its objective is also to find out the attention score of each word, but as it is present in the decoder network, so we need to be some extra careful. Decoder are auto-regressive and generates the word sequentially. So we need to put a condition for preventing the decoder from predicting the future words. For example, in this case, when computing attention score on the word chain, then we should not have the attention score of the word rouge, as it is a future word which will be generated after the word chain. A word should have only access to its score and its previous word score. So we will use a method called masking, which basically nulls out the attention score of the future word by adding a mask, which is nothing but a kind of triangular matrix having zero values in the lower half and infinite value in the upper half. So when it's added to the attention matrix, then the result is a kind of low triangular matrix with the upper half completely infinity and lower half with some attention values. The main advantage of this is when we take softmax of this matrix, then the upper half gets completely zeroed out, ultimately removing the attention score from the matrix. Now for the second module of the decoder network, the output of the encoder network are the key and query and keys, and the output of the masked multi-head attention layer is the values. Here we match the encoder input with the decoder input, allowing the decoder to decide which input from the encoder is relevant and should put more focus and importance on. The output of the masked multi-head attention layer is then added to the output of the second sub-module, and the result is normalized. This result is then passed into a feed-forward network for better representation. Output from this point-wise feed-forward neural network is then passed on to a linear layer which acts as a classifier and transfers the result into a softmax function for producing the probability score of each word, and the word having the max probability score is written as the output from the decoder network, which is basically the predicted word. Just like encoder, we can stack the decoder one on top of other and take input from the encoder, potentially boosting the predictive power of the transformer network. So that's it. That's all about the mechanics of transformer network, which uses attention mechanism efficiently to make better prediction. So thanks for watching peacefully, and I hope you must have got some knowledge about why transformer architecture is now used widely for all the natural language processing tasks, and what differentiates it and makes it outstanding from a LSTM long short-term memory network or a recurrent neural network. Thank you.